Diary, hello. It is February 2024 and it's hello from the study, and today we are looking at the S100 bus and in particular a tour of my rather wonderful Cromemco CIS00, which, as I shall explain, is sitting in an Integrand chassis. So as a bit of a recap or perhaps education, I'm first of all going to look at the S100 bus cards, and I have a rather interesting and sophisticated card with me. So this talk will be mainly talking about Cromemco cards. In other words, Cromemco was a manufacturer which started in the 1970s, and in the 1970s, so in other words, computers predating the IBM PC, there was a standard called the S100 bus, and that meant that there was a set of cards, electronics cards, with 50 connectors on each side, so 100 in total. And on that bus was typically, on that card, was typically a regulator, because the bus, as you'll see when we open up the computer here in a moment, had 8 and 16 volt unregulated power supplies. So on the card were certainly some regulators to change the 8 volts down to 5 volts typically, and a bunch of electronics. And this is an example of a card from the early 1980s, made by Cromemco. There's the logo. And this is quite a sophisticated card because it wasn't just a dumb electronics card. This was actually a computer all by itself. And Cromemco were early leaders in the Z80 based computers, and they used that leadership in actual fact to place in the latter day of their card range single board computers on a card. So this was actually an 8-port serial card. That's why it's called an octart, and it's actually got a Z80 on board, as well as some Zilog serial input-output chips, but it's also got 64K of memory, and so this enabled it to be a little computer all by itself. And indeed it runs a little mini operating system, which sole purpose for this card is actually to maintain the 8 serial port streams, and they would attach via these ribbon cables here to some special 4-way splitter cables. So this would break out into a 4-way serial port, so 4 separate RS-232 connections from that ribbon cable. Okay. So what we're going to do now is we're going to look at this Integrand, probably Integrand 800 chassis. Now I've had this chassis since I bought it new in about 1978, which is some time ago, and it had been my faithful companion whilst I was at university, for example. And this computer was just a chassis, so the Integrand company made S100 bus chassis. We're going to cover these peripherals later, but let's first look inside the cabinet. Now this normally would be screwed, but as it is, I've just there are no screws on the side here, so I can just lift off the top and we can look inside. So at the time, Cromemco made their own chassis, but they were much more expensive than other chassis on the market. Arguably they were better chassis, so this Integrand was a slightly cheaper product. I'm going to quickly just point it up at the top so you can see the details in particular. So this is the original power supply here, linear power supply. These are the cards, the S100 bus cards that sit in the chassis. And this is the area for peripherals here. Now, things have changed a lot since this machine was first built. I'm going to tell you what used to be there and what is there now. So in the olden days, this computer typically would have a CPU card. It might be an 8080 card or a Z80 card. It might have a floppy disk controller, which would control one floppy drive that would sit here on the left, and it could have one or more memory cards here. Now the memory cards typically started off, well, some of the early Godbout memory cards that I bought were 8 kilobyte cards. I seem to remember the earliest Cromemco memory card was a 16 kilobyte card, kilobyte not megabyte, so 16 kilobytes, and they did a 64 kilobyte card called the 64KZ. So that was quite a lovely card, but way more expensive than I could afford. We have a small, Jane, baby, it's live, do not touch it now. No. I know you're helping, but no one's going to be watching me now. They're all going to be watching you, aren't they? Come here. No. So, in the early days, a computer would have up to 64 kilobytes of memory, but certainly no more. So I'm going to show you what's inside the computer today, as opposed to what was in the computer in its early days. So this system, although it was initially constructed in 1978, has been steadily card replaced until it's probably running arguably one of the most powerful S100 bus configurations you can possibly get. And the actual latest cards that are here were actually manufactured in 1990. And if you remember, the IBM PC came out in the early 1980s and completely demolished the S100 computer bus market, if you like. But manufacturers held on up until about 1990. So these are these cards, as I'm about to explain, probably some of the very, very last S100 bus cards ever made. So in this system, we've got, from the back, we've got a hard drive controller. That's the Cromemco STDC hard disk controller. So that has some data and some control cables, and they feed a hard drive, which is here. I'll go into that in a second. So that's a single card, and guess what? It contains a Z80 processor and 64K of memory, as well as some dedicated circuitry to actually drive the right signal levels on the MFM hard drive that it attaches to. Then we've got two cards here. One of them is an octart behaving as an 8-port serial card, and the second is another octart with no cables attached to it. So you can see that the first one here actually is called ZIO2. So that's being used to just be a Z80 processor. So this is like a satellite processor sitting on this motherboard, this passive backplane. And the idea of this card here is that it can act to run Z80 programs. So it's got its own Z80 processor, 64K of memory, and CPM or CDOS, which was Cromemco's version of CPM, was an 8-bit 64K max 64 kilobyte operating system environment, and so that can run programs from that era. So if you can remember things like SuperCalc or various screen editors or some rudimentary spreadsheets, that could be run on this card. This second card does have a single ribbon cable here, and that ribbon cable is going to a second serial port at the back of the computer. So then we've got 3 cards here, which are the memory cards. Now, like I say, a regular S100 bus computer might only have 64 kilobytes of memory. Each one of these cards is a 2 megabyte card, and that is absolutely huge. So if you do the maths, it's tens the size of a 64K card, obviously. And at the time, these were priced, you know, at a eye-wateringly high price. You couldn't imagine the cost of these cards. I've only been able to afford these cards because these cards were bought in 2007, 2008, when they were being sold off from a NATO sale. So a NATO supplier sale. And lastly, you've got these 2 cards here. You can see that. These 2 cards are an XXU and an XMU. The XXU is a Motorola 68020 CPU card, and that's mated to an XMU, which is a memory management card. And if we just put along a bit more towards the back of the chassis, you'll see that we've got a linear power supply here. I've already commented it was 8 and 16 volts. I've put a PC power supply in here, and the idea of the PC power supply is that it feeds the 5 and 12 volt rails in this peripheral bay here. So this peripheral bay here contains, let's see if we can look up from the front and see if we can see things in more detail. So this has gone through several iterations, because originally this contained a half height 5 1/4 inch hard drive and a floppy drive, 5 1/4 inch floppy drive. But as of today, that hard drive has been replaced by a hard drive emulator. So sitting in there with lights are flashing and an Ethernet connection, I don't know if you can see that wire, that's a black Ethernet wire, is a Linux computer, and that Linux computer is emulating a hard drive. And next to it we've got the HXC floppy drive emulator. That's emulating 2 floppy drives. It's actually emulating 2 8-inch floppy drives. And lastly, we've got this specialized Japanese 3.5-inch drive, which is also emulating an 8-inch drive. So effectively here we've got 3 8-inch drives, and here we've got a hard drive. And in S100 terms, I don't think you can get much more state of the art than that. That's like rocket science in S100 land. Whoops, and finally I completely forgot to mention one of the most important cards in the whole system, which is the floppy disk controller. Now this is the 64 FDC-X floppy disk controller, which was the best controller they ever made. So the history is they started off with a 4 FDC floppy disk controller, and that could only do single density floppies. So this floppy drive that was here originally, which is a 5 1/4 inch floppy, only had, I remember the number, when it was formatted, it had 79 kilobytes of information that could be stored. And that was single-sided, single density. There was no reason why you couldn't have a double-sided diskette drive, but that was obviously much more expensive because the drive had to have heads on both sides of the diskette. So the first floppy disk controller, the 4 FDC, the first floppy disk controller could actually do double-sided, but then they produced the 16 FDC controller. So the 16 FDC controller had, like the 4 FDC controller, had 2 ports, one for the PSI drives and one for the regular, if you like, Seagate drives. So at the time, PSI was a company, an American company, that produced very, very fast floppy disk drives. They actually had a voice coil actuator, which was something that hard drives had at the time. And those hard drives with a voice coil actuator could seek very quickly. So PSI was unique in the industry because they produced 8-inch floppy drives with this voice coil. So there was one voice coil and it controlled a set of dual drives. So that's effectively 4 sides, 4 heads on one arm with a voice coil actuator. Now those drives were frighteningly expensive, and it turned out in the long term quite unreliable. So you went from 4 FDC to 16 FDC, and when the writing was on the wall, i.e. that PSI drives were not the future because they were A, expensive, and B, slightly unreliable, Cromemco switched with the 64 FDC to have the interfaces here. This was an 8-inch for the 8-inch drives, but a standard, if you like, Seagate interface, and this was the interface for 5 1/4 inch drives. Now they were pretty much the same interface, but with different pinouts, which was quite irritating. At the last sort of gasp, Cromemco also produced the 64 FDC-X disk controller. And I'm not sure that was anything more advanced than 64 FDC, but maybe the components were slightly faster in some respects. Now, that that board, the 64FDC and 64FDCX, does not contain a Z80 computer. It does, however, contain a Western Digital, I think it's a 1771 floppy disk controller, and that was the kind of guts of the whole of this card. And I'm spending a lot of time on this card because it was probably the key card of the whole system, because not only did it have a disk controller here, it had a serial interface. So when you bought an initial system, all you would need would be the CPU card, the floppy disk controller card, and a small amount of memory. So it really was one of the key cards. Now this card also is interesting because it has a ROM on it, a read-only memory, and that contains the RDOS, the Resident Disk Operating System. So when a Cromemco system starts up, it jumps to C000, that's in the Z80 68000 world. And that ROM is present, and the RAM that would be there has to be disabled for the purposes of the boot. Okay, in this part we're going to actually start up the system, and the first thing we need to do is start up the disk emulator. Now, if it had been a real hard drive, we wouldn't have to do this. This would be powered from that PC power supply inside the chassis, but we've actually got a much more flexible David S100 MFM hard drive emulator. I urge you all to check it out. It's a fantastic product by David. We're going to go into the message of the day. So this is a Linux console to a Linux computer connected to some hardware, which is going to emulate a hard drive. So I'm going to cut the message of the day because that's where I put the instructions if I forget. And I should just need to run this program here. If I cut that Unix script out. You'll see we are going to go into this directory and we're going to run this program. In fact, we'll just have a little look at these programs. There's a bit of an aside, but it's documented anyway. So this is the emulator directory, and David's card is actually using the GPI pins on a BoneSys emulator, which is connected to this hardware card, and so it talks through its GPIO pins, and he's written some code to emulate the interface, which is just amazing. Look at the directory, let's have a little look. Yeah, so there's various different releases of the code, and if I do the cat command, you'll see that we're going to execute the setup emu program, and then we're going to run his emulator with a particular file. So I've got a number of disks. This is disk D45. We're going to his emulator could potentially support 2 drives. We're going to call it drive 1, and this is simply a huge file, well, huge by 1980 standards, which contains a file which will be interpreted by the Cromemco computer as a hard drive. Now, if you join the Cromemco GitHub and the Cromemco Google group, you will have full access to all of these resources. I'm going to show you the screen. There's an ASCII file which describes disk D45. So remember, we are looking at disk D45 here, which is what it sounds like. There are at least 45 hard drives in my catalogue, which this one is exposed to the public. So this has got on it a number of partitions that you can see here. And for example, the ST, so in Cromemco terms, remember it was an STDC disk controller, and the partitions are STD0 and then a number. So you'll see that the first partition, which is STD0, is the Cromix 167 level operating system for 68,010 computers. That's a scratch volume. That's the Z80 version of Cromix. Remember, Cromix is the Unix-like operating system that Cromemco first made for its Z80 computers, and that's a version for the Z80 computer. I can't boot it because I don't have a version of the right hardware to boot the Z80 processor. So that partition just sits there. This is another partition. This is a recovery partition if I was to screw any of these partitions up. And partition 4 is the one we're going to use because we've got the fancy XXU CPU card with the Motorola 68020 processor. So that's the partition. Partition 4 is the one that we're going to go to. Okay, so let's start up the emulator, which would be to run that program. And it was done a password for this computer. Okay, so now we'll scoodle that off to the left-hand side, and we are going to be looking at a USB to serial interface plugged into the back of my workstation. So the workstation sees that as /dev/tty.da, and I'm going to use the screen command, standard Unix command. With that device, space 9600 means baud rate of 9600, and that's the going out of my computer with a USB interface through some electronics to convert it to an RS-232 serial interface. Now I'm going to go power on the system. One moment. Now let's escape to get out of that. So this is slightly unusual in Cromemco terms. So in the usual case, Cromemco computers would require a floppy disk controller with something called RDOS on that controller. So RDOS was a resident disk operating system. So when you have a Z80 or combo Z80 68000 card, when the power is switched on to the Cromemco system, what must be true is that the floppy disk controller ROM at hex C000, so in the first 64K space, at hex C000 must be the RDOS ROM, and the Cromemco CPU would jump to C000 and read the Z80 code at that point and execute the Z80 code. That's the case for all Cromemco computers, except that in the late 1980s, when they introduced this special 68020 processor card, which is part of a 2-card set. So there's one card for the CPU and one card for the memory management unit. On board that CPU card is its own, I think it's not just 8K, I think it's a 64K. I mean, that's just a massive ROM, which does almost nothing as far as I can tell. I mean, there are a few commands. So what I'm trying to say is, in the olden days, you would boot via the Z80 processor to C000. Here, you don't do that. When this XXU card starts, it runs from a ROM on its own CPU card. And that's why you see this prompt saying DDoS. Like I say, there's hardly any commands here that make any sense, and it's doubly insulting because this ROM is quite large. So exactly what it's doing, who knows, but it will do a boot. So we can do a boot to a floppy, or we can do a boot to a hard drive. So remember that the partition was STD4, so you want to boot to ST4. So we're going to boot to ST4. So you can now see the hard drive emulator working very hard. Now you can see the memory test, which is so it's read something from the hard drive. It's now effectively read the operating system called Cromix.sys. And now it's booting that operating system. So first it did a test by memory blocks. Now you can see each of these pluses is a 16K space. So this is not in Z80 mode. In fact, this card can't do Z80 because it doesn't have a Z80 processor. But on the dual processor cards, it's a toss-up as to whether it was doing this in Z80 or 68000. Okay, so we're logging in. Now we've actually logged in. So we're now running on Cromix 172, which is the last version of Cromix that I imagine ever existed. The date and time are wrong because it was only a 2-digit date code, and that can't be fixed on this system. We're now logged on, fully logged on. I think you'll see that there's an error message here. This error message relates to the fact that there are 2 Octart cards installed. One was behaving as a 8-port serial card, and one is behaving as a satellite Z80 processor. And the Octart card, I think, is busted. There's something wrong with it. I've not diagnosed it yet, but it won't stop the demonstration for the purposes of today. So many of the commands you're about to see are Unix-like commands. Cromemco always said that their product was more friendly and better documented and more easy to use than Unix. And so, for example, the cd command is in fact the D command. So if I D to the root file system, not cd, you have if I do ls-l, you'll see we have the following directories, which have gone off the screen. So if I do ls-l and pipe, since it's a Unix system, to the more command. So we've got binaries are in the bin directory. Command programs like shell programs will be in the cmd directory. If you want to mount a file system, then you mount it onto a file. So I've created a file called code, and I can mount another disk partition onto that, and then I have a /code. That's a text file that I just put in there to say what I'm running. Cromix.sys is the operating system, and as you can see, it's about 120k, thereabouts. DA, DB, DC are files that I would mount floppies onto. Dev is the devices directory. EQU is storing programming equates. ETC is etc., so it contains some low-level files that are used by the system when it boots. Gen is the directory where the operating system generation files live. These are more places where you can mount other partitions onto. RAM is a RAM disk. Do you know what? It's an error. That's not a RAM disk. That's a file. So that's a wrong. That's something that's wrong there. I can get rid of that in a second. TMP is the temp directory, and TT is a file that I think I was using as a directory. So I can do I can have a look in TT, for example, and there's a few bits and bobs in there. Do you know what? I'll keep that. There's some things I was actually using that for some development purposes. I'd really like to keep that. Let's again. Let's just do some housekeeping, shall we? I'm pretty sure I'm never going to need these HD files here. So if I do ls of HD star, I get HD3 and then a number. So if I do ls of HD3 and then 2 to 7. Yeah. So if I do del of HD3 2 to 7 star, and do ls myself. Now fits on one screen. I'm going to delete RAM because that's not needed, and I'm going to say create. Now there is a RAM. So if I go into the scripts directory and have a look, these are all the scripts. Again, these are scripts I've written over many years. I think make RAM. If I type out the make ram.cmd script. Okay, so This is the make RAM script. It says there's an echo command to print something out. It creates a RAM disk of 128 kilobytes. If there's an error, it quits. It then makes a file system, a Cromix file system, onto that RAM disk, RD0, device RD0. These parameters are necessary to say store at most 20 files and don't have any boot block area, because this isn't going to ever be booted from, so that would just be wasted space. If that works, it mounts it, it shows the owner, and then copies files into it. So let's run that, shall we, and see how it runs. So it is /cmd make RAM. So now we've made a RAM disk. If I do a mount command, you will see that we have the RAM disk is mounted onto /RAM. And if we do the mode command, that is should be coming from the /RAM, not loading from the hard drive. In fact, this is good to be able to prove that. So here's the hard drive. If I type the mode command, you'll notice that this simulated hard drive doesn't move because the mode command is coming from /RAM. So nice to be able to prove it. Okay, so let's have a look at a few other things. If I go into the gen directory, I'm going to spell it right. By the way, the speed of the system is phenomenal. This system is going so much faster than any other Cromix system I'd ever use. So growing up with a Z80 and 68000 Cromix system, when you typed in any commands, you'd never get this speed of response. Firstly, because you're dealing with 68000 processor, which is probably about 4 times slower, so a quarter of the speed of this processor. And secondly, with a real spinning hard drive, the data was being transferred at a much slower speed. This simulated hard drive is very fast. So those two things contribute to actually what's an incredibly fast performance. I'll show you, if we do D, shows the directory, we're in the gen directory. These libraries here are what's needed to generate a new operating system. And the sysdef command takes a text file and these libraries and generates a new operating system. Cromix has got a full help system, so if we do h-space sysdef, we can probably get some help on that, right? So it says sysdef generates a configuration file for the Crogen utility. So sysdef is taking the text file and converting it to a binary file, and then the Crogen command takes that binary file and generates the operating system. So let's do a little space around maximum. And so it's got some definitions of what's in that sysdef file. Quit out of that. So if I do ls minus ltr and look at the last sysdef file that we've used, it's in the wrong sequence, isn't it? Here we are. Here's the one from the 5th of February 2024. So if I do a more of 2024.0205.sysdef, we can look at that file, and this is the operating system configuration file. So we can have up to 16 to 256K units. Again, these figures are so wildly larger than the original 64K that, you know, if you were showing this to someone in 1980, they'd be going, "Oh, I can't believe this. This is like science fiction." Of course, now 256K of memory, or even 2 megabytes of memory, is a ridiculously small number. I mean, PCs can have, 128 gigabytes of memory, not 128 megabytes, gigabytes. In other words, 1,000 times more memory than a system of the 1980s. Anyway, to continue, so these are the configurations of the devices in the operating system that we are saying are there. So, for example, to say that we have got a character devices here and block devices here. So we're saying we've got a floppy disk driver, we've got a uniform floppy drive, which is kind of sort of more Unix-like because it uses consistent sector sizes, and we have a RAM disk here. And then we're going to say, where do you want to boot this system to? We want to boot it to major device 6, minor device 4. So by the way, this is a full help system. We should have, more. We don't have, this is the help for the more command. So I should be able to do backwards. No, but I can go to the beginning. I thought it was an help command. It's got a better positioning than this command. They're the block drivers. There's the root device, and then we've got some of these systems. But we can change this buffer. There's various different buffering parameters we can change here. So when that's all been done, you run the crogen command, which I'll just type out, and that effectively links the system together. Again, this isn't going to work. I need to more. Let me just more of crogen.cmd. So we're going to systef these files, and then we're going to link 68 them here with the IOlib and the crolib, and that generates a new operating system here. Okay, so you've seen how we would generate a new operating system. Let's go into the bin directory, and in this bin directory is Cromemco supplied files, but also I've created some various directories, because in here are things like JRT. If I see JRT here. And if you remember back in the JRT is a Pascal compiler. So this is the JRT Pascal compiler, for example. If I go into the Fortran directory, so the up arrow is to go up a directory. So now we're in that directory. That is the CPM Fortran compiler, if you can remember 4.com. So when I type in 4, if I'm lucky, yeah, okay. It's not really telling you very much there. That is the right response for the CPM Fortran compiler. It's just a star. It might give you a message of the manufacturer of the compiler. It's just not that helpful. L80 was the CPM linker. Might come up with something. That will come up with copyright. Yeah, link 80. Okay, that's a bit better. These are the CPM, i.e. Z80 programs, and how is it working? Because this system's only got a 68,020 CPU. Well, that is where this superbly clever system that Cromemco made comes into play, because it uses the satellite Octart Z80 card to run those CPM programs. So it's just so clever. So I can run any CPM or CDOS program, and that's how, when I type FOR, the system said, that's a Z80 program. You need to ship that whole program off to the satellite processor, run it in the satellite processor, pass any output back through to this TTY screen and display it here. We're in Fortran. If I go up a level, so if I look at other bin files in this directory, we have got the C compiler, for example. So if I just type C, that will be the 68,000, and I do a version c.bin. That's the 68,000. That's the strings command on this. I can remember. Strings. There is not a string. No. Perhaps I should write one. You'll see there's commands like ftar and there's tar. There's rcopy, which is to copy block devices. We've got directories that I've created. This is compiler basic. This is the CDOS operating system. This is JRT Pascal. This is a directory for screen editors for a particular terminal. So in the early days, ASCII terminals had their own escape, what they call escape sequences, to enable them to do things like address the cursor, put the cursor on a particular part of the screen. And every terminal manufacturer did things slightly differently. So if you look in the etc directory, there's a file which tells you what terminals are attached to what systems. And we see here that we've got a terminal of type M100. So the idea in the latter days, not in the early days, you had something called like WordStar word processor. You'd actually have to patch the binary and put the right escape sequences in, or have WordStar patch it for you. But in the later days, you had a programming interface called term caps for this system. And there's a programming call that says, if I want to, for example, delete a line or erase from the cursor to the end of the screen, please, I know that I'm at M100 terminal, please tell me what escape sequence that would require. That was a step forward, but of course, hardly any programs use that interface, but it is there. So yeah, we've got an M100 interface, which is effectively a VT100 program. I said there was a help system. If I do help of ASMB, which is the Z80 assembler, have I put that in there? That would have been, no, that wouldn't be the help of C. Help of LS. So you see that Cromix does come with a help command. You can add to this set of help files yourself. So I was hoping I'd added some of those in, but I haven't. So this is just showing that the ls command comes with these options. I can do H at this screen, and we can see that this is the inbuilt help system that allows me to go up or quit or find some stuff. So I can press a space key. I think I can go back. Yeah, so we're going back. Okay, I think that's enough for now. If I do ls minus l of /, we've shown you we had various different directories. I think I'll probably just show that the fact there's a dev directory of ls minus l of /dev will show you that this has got a number of devices in that directory. And just like Unix, a device is a physical bit of kit. So the std4 is a partition, std5 is a partition, std6 is a partition. And if I do disk info, I can show the whole disk at once. So std31 is the partition that means the whole disk. So if I do disk info of std31, I will look at the whole disk, and it says, oh, you've got a disk which has got, again, for the time, this would be impossible. You've got a disk which is actually 1,500 cylinders. It's the total size of the disk is 245 megabytes, of which partition 4 is the one that we booted, if you remember. That's a 10,000 kilobytes, which is 10 megabyte partition, which for those days was amazing. This is the alternate track table of the hard drive. It's blank because this is being emulated by this Linux computer, so there's never going to be any problems. But in the olden days, you'd buy a disk and it would actually have some defects on it. And the idea was that you'd keep a portion of that disk and call it the alternate track table would map faulty tracks in the main drive to a special part of that disk which you would have for alternate tracks. So as an example, let's suppose you had a disk which was actually 600 cylinders or tracks in size. You might say, well, I'm going to use between track 0 and 580. And from 581 to 600, I reserve those as alternate tracks. A manufacturer might say, oh, well, track number 1's got a problem. So you'd say, okay, well, I'll map track number 1 to the alternate track of, in our example, 581 was the first one. So when the computer tried to go to track 1, it would first check the alternate track table. Now, an alternate track table would say, wait a minute, cylinder 1 is completely rubbish, so you need to go instead to cylinder 581. So that's how the alternate track table works. It was a mapping of bad areas of the disk to good areas of the disk. Okay, I think we're done. It only goes for me to shut the computer down. I'm going to see who's logged on. There's only me logged on. So who am I? There's only me. Oh, this is not working well, is it? Let's try who. There's only me logged onto the console. I'm going to shut the system down gracefully, which is actually this command. And we're done. Thank you very much for watching.